Okay, so let's look inside an excavation. So we said the excavation is digging a site systematically, carefully keeping track and records. It's not just digging, you're actually almost dissecting the site. You're taking it layer by layer, you're figuring out where things were found, and you're providing a lot of documentation. Okay, there are different ways you can do this. And kind of a very broad way to paint a picture of an excavation strategy is horizontal and vertical. Obviously, you use a combination of both if you're really digging in an archaeological site. But let's just take a look at what each kind of excavation can tell you. All right, this is obviously here a vertical strategy, right? So this is the top of a tell, digging all the way down to the bottom of the tell. And you can see that you get a small window into the different layers of the past. So you only expose a small area, but you're able to go from the top to the bottom and get the different time periods. So vertical excavation is excellent for looking at questions about changes over time. How did things develop? How did diet change over time? That kind of thing. This is a horizontal excavation, so it's one layer, but it is a wide exposure of that layer. So this excavation strategy, you get a lot more detail about a certain time period. The problem or the drawback is you're not going to get information about other time periods. So they both have their benefits and their disadvantages. Okay, once you've excavated, you're going to find things like pottery and stone tools and things like that. And these are classified in different ways, right? So anything that humans make or change is an artifact. So a stone tool, a piece of pottery, those are artifacts. If an ancient human, though, took a stick and that stick happened to just end, they made it, that stick just happened to, let's say the human didn't take it to the site, but let's just say it rolled into the site. Would that be an artifact? No. If an ancient human took a stick and sharpened the end to use as a digging instrument, would that be an artifact? Yes. So it's anything that's made or modified by humans. What about animal bones? Are animal bones artifacts? Well, they don't, unless they're turned into tools, they're not. They're what we call ecofacts, right? That is, they provide some information about the environment and also their diet, but they're not actually deliberately manufactured or changed by humans. Features are large artifacts that can't be moved, like walls, floors, parts of a structure. Those are the three basic things you're going to find: artifacts, ecofacts, features. Okay, we've looked at stratigraphy already, right? We've talked about the different layers at the site. Now, for example, this layer over here, this white layer, is this layer older or younger than this layer beneath it? What would you think? I think most of you would probably guess that the yellow layer was older and the white layer was younger. And that's exactly right. And this is actually called the law of superposition. Right? The superimposed layers, they build up over time. So when you're digging out of the site, you're actually digging backwards through time. You're digging down through the most recent to get to the oldest. And so understanding stratigraphy is very important in archaeology because you can tell if something is older or younger. All right, let's look at this pit. Pit is secondary context, you guys probably remember. This pit you can see, and the layers on either side of the pit. Now, is this pit younger or is it older than this material? Well, if you think about it, the pit was dug into soil, right? So actually, the pit is younger because these layers used to exist all the way across. Then later people dug into them, removed that soil, and threw trash in there. Right? So if you were digging this site, you would want to dig the pit out first. You always try to dig from younger to older. You get rid of the pit, and then you would dig the material on either side of it. Being able to tell that something is younger or older is important. Now, just from looking at this stratigraphy, could you tell how much younger this white layer is compared to that yellow layer? You couldn't. right? You can only say that it is younger or it's older. Now, this is called relative dating, because relative to one thing, it's older, relative to another, it's younger. So stratigraphy is a kind of relative dating. Absolute dating is different. With absolute dating, you actually get a date according to the calendar. And I'm sure you know of several dating techniques. What do you think is the most common dating technique found today? That, when you read scientific papers, they always talk about this dating technique. Some of you might say radiocarbon or C14 dating, and that is one of the most common forms of dating. So let's take a look at some absolute dating where you actually get a calendar date. A really good way to date things is with dendrochronology. This is using tree rings. Well, how could you use tree rings to date something? Well, you use it to date an ancient piece of wood. How does this work? Well, you can see that the light-colored band, the dark-colored band are one ring. Typically, how many rings form on the tree per year? Usually it's one. Right? So one ring per year, which means that you could count the rings back, and you're counting backwards in time. Now, the rings are different thicknesses. They're thinner or thicker in certain years based on the moisture, on the rainfall. So in a wet year, you'll get a thicker ring. In a dry year, you'll get a thinner ring. So the rings are not always going to be the same thickness. That's important, because what you can do then is you can build up a master code or a master sequence. So let's say you have a modern tree, and it's got tree rings that extend all the way back to, let's say, 1790. Then you find a piece of a much older tree, and you can match up the rings, and now you've got a sequence that goes, let's say, from 1850 back even further. Then let's say you find a timber from an old structure, and the dates and the rings go back even further. So now you have a sequence of rings, and because the rings are different thicknesses, if you found a piece of a tree in an archaeological site, you could try and match it up with the master sequence, and the very last ring on that piece of wood would tell you when that tree was cut down. So you could actually get a date to the specific year based on dendrochronology. Right? Sometimes ancient people were very nice to archaeologists, and they actually put the dates on things. Like the Maya, they dated many of their monuments, and because, as we'll find out, archaeologists can now read Maya glyphs, and we know the dates, and you can actually date many of these Maya monuments. That is a form of cross-dating. Another good example would be, and I sometimes ask this, but this sort of artifact, people don't always carry it around anymore. But let's say you found someone's clothes in the bottom of the ravine, and you want to figure out how old the clothes were. Is there anything that you could use? You might date it on the style and things like that. But what would give you a really good date? Any kinds of artifacts in there? Maybe they didn't leave their phone in their jeans. But if you found a penny or a dime or some other coin, you'll have the date on the coin. That's another good example of cross-dating, dated coins. Right? Okay, C14 or radiocarbon dating is probably the most common form of dating. Well, how does it work? Well, many of you have probably taken chemistry, and you know that carbon, or ordinary carbon within the nucleus of a carbon atom, there's 6 protons and 6 neutrons. There are also typically 6 electrons, right? So this gives it its chemical properties. Right? The protons and the electrons determine kind of the way the atom will interact with other atoms. Well, you have isotopes of carbon. This is carbon that still has 12 protons, but they have extra neutrons. And the extra neutrons don't change the way it behaves chemically. It's still carbon, but it's heavier than carbon-12. Right? So if you have an atom with 2 extra neutrons, its weight is not going to be 12, it's going to be 14. Right? So that's carbon-14. Carbon-14 is radioactive, like uranium or plutonium, which means that it breaks down over time. It's a radioactive isotope. Now, it's C14 is found in the atmosphere. It's found in the water, in the soil, in the plants that absorb the water and nutrients from the soil, the animals that eat the plants, the other animals that eat those animals, and us. So anytime we lose carbon-14, we replace it through eating and drinking and things like that. However, when we die and are buried in the ground, we no longer can replace the C14. And over time, slowly, the C14 is going to break down. As it breaks down, it disappears. And so essentially the way carbon-14 dating works is the older something is, the blank amount of C14 there is. What do you think? If you said the less amount of C14, absolutely. Right? So by figuring out how much C14 is left, you can then date it. Now this is great, but if you go back earlier than 50,000 years ago, all the C14 will be gone. There's no way you can date it with C14 anymore. That's a little bit of a problem. So what do? Use a different isotope. Use an isotope that has a longer, what we call half-life. It takes longer to break down. And radioactive potassium is a great method to use, right? So potassium argon dating, you can date something, it's volcanic material usually, that you can date it to millions of years ago, right? So there's different kinds of absolute dating techniques, right? We talked about cross dating, dendrochronology, radiocarbon dating, potassium argon dating. Those are all absolute dates because if you send a sample to the lab and you said, please measure the amount of C14 in the substance, they're going to tell you how much C14 is left, and they're going to give you an estimate of the date. They'll say, oh, this is, dates to 3,000 years ago, plus or minus 60 years. That's an absolute date. All right, let's look at some more relative dates. We said stratigraphy is an example of a relative date. Let's look at another one, seriation. This was a really clever method that was invented by a famous Egyptologist named Flinders Petrie. He was in Egypt in the late 1800s, early 1900s, and he was digging a series of ancient tombs in Egypt, tombs that predated the pyramids. There was very little writing or no writing in these tombs. And because these tombs were not on top of each other, they were separate, he had a hard time figuring out which tomb was earliest and which was latest. So what he did was he took the same kind of pot from the different tombs, and he could see that they were different in their shape, they were different in terms of the handle, they were a little bit different in terms of the mouth of the vessel. And what he tried to do is to put these into a logical order, right? What pot would come first? What pot would come second? What pot would come third? Right? So see if you could do this, right? Logically, which pot of all of these would come first? Which pot do you think would come next? Which pot would come after that? Think of it in terms of evolution, slow change over time, right? You're looking at a progress and a progression of the style of the pottery. Well, what Flinders Petrie did is he assumed that the large vessel was earlier, right? He said, in his mind, it made more sense that a handle would get smaller and turn into basically just a small little thing on the top here than for this little decoration to get bigger and turn into a functional handle. And he happened to be correct. Well, okay, so if this is the earliest, what comes next? Well, this is very similar to it, but it's a little bit narrower. Okay, and this one is similar to this one. It's more similar to that than this is to that, right? But it's narrower. And then finally you would have that. So he was able to put these pots in order based on style. He put them into a series, and this is why it's called seriation. You could do this. I've had students do this with old Coke bottles. You could do it with cars. You could do it with the icons on superhero outfits, right? So here's the logo from Superman. Pause the video for just a second and see if you could kind of roughly figure out what the oldest one oldest logo would be, what do you think would come next after that, etc., etc. See if just based on the style you could put them into some kind of order, and then unpause the video and we'll talk a little bit about it. Okay, how'd you do? Well, hopefully you were able to figure out that this is the earliest, it's the most dissimilar, this comes next, right? This comes after that. That's pretty easy because very similar shape. And then what comes after that? Well, then you get kind of this sort of style that you can see over here, slowly morphing into what we know today, right? So you can see how things changed over time, right? And if you took this and put it over here, it will look out of place. Right? Everything in the series has to share characteristics of what comes before and what comes after. You can do this with other kinds of artifacts like clay pipes that are found in colonial North America. You could do this with the rim shapes of pottery. This is a cooking pot, the kind of cooking pot that you would find in ancient Israel. And here's the rim and the way the rim changes shape over time from the very early period to a later period. Right? So this is relative dating. Again, if you find, putting them in a series, you can say that this pot is older than that pot. You don't know how much, though, unless you use C14 or another kind of dating. So that's relative dating. Right? Okay, well, now let's get into our first big question. Now, hopefully you have some understanding of how archaeologists do what they do. It's very kind of, a whirlwind tour of archaeology. We have a whole class on archaeological methods if you're more interested in how archaeology works, but it gives you a little bit of an idea. And we're going to talk about archaeological evidence throughout the semester. But now we're going to get into the first big change in human history, agriculture, farming. We're going to talk about what agriculture actually is, what farming is. But we also have to talk about what life was like before agriculture. Before we do that, let's talk a little bit about dates. Because sometimes when you're doing some reading, people might talk about years ago. And years ago is not BC. Right? So if, for example, if you are reading 4,000 years ago or before present, it's another way of saying years ago. 4,000 years ago, you have to go about 2,000 years back to the year 1, and that leaves 2,000 years more. You go into BC from AD, and you are in 2000 BC, right? So the calendar date, AD BC, is not the same as years ago. Just keep that in mind. That's something we can review more as well. I'm not fixated on dates in this class, more understanding roughly how old something is and the things that happen along the way. Let's go back 12,000 years ago. What would 12,000 years be in BC? Right? Because right now we're in AD. How do we get to BC? We have to go 2,000 years back. And then we have how many years left? 10,000. That would be 10,000 BC. Right? So around 11,000 BC, 10,000 BC, it is the end of the Ice Age. If you've ever seen the movie 10,000 BC, it's not a great portrayal of the way life was back then. But we're going to look at the way life was back then. Right? The Ice Age. This time period, according to geologists, is called the Pleistocene. Right? The archaeological cultures are called something different, as we're going to see. But the Pleistocene is the Ice Age. So up until about 10,000 BC, you have a much colder environment than you do today. Right? Average 12 degrees colder Fahrenheit than it is today. And that changes things a lot. Michigan, if you were in Michigan and Allendale 12,000 years ago, you would be standing on top of a glacier, right? It was completely covered in glaciers. You only get an ice-free area of Michigan around the end of the Ice Age, right? Which is around 10,000 BC, roughly. So it was 12 degrees colder. The ice caps were much larger. What about the sea levels? Were the sea levels higher or lower? They were lower. Right? If the ice caps are bigger, it's taking water from the oceans, and the ocean levels would be lower. Now, if warmer water that we have today compared to colder water, what are you going to have happen more in warmer water than you would in colder water, right? So imagine you are heating a pot on the stove. What starts to happen, obviously? You start to get evaporation, right? So you're going to have more evaporation in warmer water. Because it's colder in the Pleistocene, you have less evaporation. If you have less evaporation into the atmosphere, what are you also going to have less of? If you said rainfall, you were right. You're also going to have less rainfall, right? So the Pleistocene, on average, was colder and drier than it is today. Okay, so we're going to stop here, and we're going to pick up with this in the next recording.